Today we're going to talk about feedback control. This is another relevant topic for aircraft design. We're not going to get into much depth. There are multiple classes on controls and even a full semester course just on aircraft controls. And this is also not my area of expertise, so it's going to necessarily be fairly basic, but good to have at least some idea of the basic principles here and what this topic is about. So let's start with some familiar examples, things that you've seen before. One is here on the left, a cruise control in a car. You could also think about it as you as the controller when you are trying to maintain a speed. So if you're trying to maintain a speed or the car's computer is trying to maintain the speed for you, we have some set point, we call this a reference point where we want to hit, say it was 65 miles per hour. And if we are below that, then of course we were going to speed up or push down the pedal. If we're above, then we're going to ease off, right? And so they're at a basic level, that sounds not too difficult, but there's some tuning, there's some design involved. So for example, we call this the gain, and we'll see this a bit in a minute, but how fast or how hard should I push on that gas? So if I'm too slow, you could imagine a scenario where I just push down too hard, right? Every time I react too hard to the error. And so I speed up way too fast, I pass my speed, and then I slow down, and potentially that's even an unstable process. At the other extreme, maybe I react really slowly. I'm going too slow, and I barely increase how much I'm pushing on that pedal. And so I would get there eventually. However, the problem is that slow speed isn't resilient to disturbances. So as conditions change, right, I'm going so slow that I can't react to my changing environment very well. So there's some balance point that I want to achieve and having this respond well. And maybe you've had cruise control in your car that didn't respond as well as maybe another that you've driven. On the right, we see a thermostat. Here's another example where I would set a temperature, and if the temperature is too cold, then let's say it's heating mode. It's too cold, then we're going to turn on the heater, turn on the furnace to heat up the home. And then once we reach past a certain temperature, we're going to turn it off. A main difference in this process as compared to the other is that I could control this throttle continuously, right? I could go up and down and how far I was pushing the gas. Whereas in the furnace example, the furnace is either on or off, right? So we just turn it on for a set amount of time, and then we turn it off. There's no it's not on halfway or something like that. This is used in many spacecraft controls, whereas the left case is maybe more in aircraft controls. So many spacecraft will have, say, rocket thrusters, and those are either going to be on or they're going to be off. And so there are techniques like bang control is what it's called, to handle these kind of scenarios where it's either just on off, not a continuous variation. So like in the heating example, we don't try to just turn it on and off. If we're just off by the temperature a little, we're going to set kind of this deadband, if you will, what it's called, so that if the temperature drops a little, we're not going to do anything. But if it drops, say, a full degree or 2 degrees or whatever the set point is, then we turn the heater on, and we don't turn it off right when we reach our desired temperature. We're going to wait maybe a degree and then turn it off. So there's this deadband region where we don't do anything. Okay, so one approach to controls, I guess, is to do what's called open loop control. So open loop control means that we're going to sense, or we're not going to sense any information and feed that back into our controller. We're basically going to design it beforehand. So in other words, let's say I've got my airplane here. I know where I'm at and I know where I want to go, say this waypoint, and I could design a controller that's going to adjust, my ailerons and my elevator settings and so on, so that I could achieve this type of turn. This could work well if everything was deterministic. The problem is, in real life, right? What if there's some wind to the left, and I programmed this so I'd perfectly get there if everything was ideal, but because of the wind, I end up over here, or the atmospheric conditions are a bit different. the density is different. My turn doesn't respond quite as much as I thought it would. And so these kind of things are going to deviate in a real world scenario. So again, ideal scenarios could work well. And so it really depends on your application, how much uncertainty and deviations there may be. You could see, for example, in the previous ones that we discussed with the car, an open loop control is not likely to work very well. Meaning if I have a speed that I'm at and the speed I want to go to, I could design, here's kind of the ramp rate of how I'm going to push on the gas, but depending on how much weight's in my car, the type of road surface I'm on, if I change my tires, how much wears on my tires, all these things are going to affect how my car is going to perform. Maybe my engine, the temperature of the day. So in general, I'm probably going to be quite a bit off. Similarly with this thermostat, if I just tried to do a pre-programmed process and didn't sense where I was at, then, as I changed the home and I added insulation, or there was a door, some windows were open, or it was just a really cold day, these things are not going to be taken into account because I'm not sensing the information. So this is not going to be a common strategy, except for maybe in simplistic cases. Instead, we're going to use what's called feedback control. We want to do something, right? Make a control input and then sense what happened, right? So in the thermostat example, I'm going to put in some heat, but I'm going to sense what's the temperature. Is it changing? Do I need to keep going? Same with my speed in my car. I'm going to put on the gas. I'm going to sense, am I getting close? Am I not? Same with the airplane. I'm going to sense what's my position now, where's the position of where I need to be, and make course corrections along the way. So I'm getting feedback throughout this whole process. So this is called feedback control. We usually illustrate this with a block diagram. So this would look something like this. Here's my dynamic system. So this is your airplane or whatever it is, right? It's got some governing equations and things. And coming in, and these are just the typical symbols. U is the input. These are the system inputs. And Y are my system outputs. And if I had an open loop control, that's going to be it. I'm going to try and design a set of inputs, pass them through my system to achieve some desired set of outputs. And hopefully, it just works. But in general, right, it's not going to because of the disturbances. So we want to take this output, measure it, right, see what's going on, and pass that back. We're going to feed it back and compare it to what we wanted it to be. So in this case, say R is what we'll call the reference input. This is the reference input, because I should put system here to distinguish the system outputs. Reference input is our desired target. So in the cruise control example, that might be the 65 miles per hour. So 65 miles per hour is my reference input. My system output is what I'm actually measuring. So I'm measuring 60. So I'm going to feed that back and compare it to this number to see how I'm doing. And so we draw this as a summation. We put a plus and a minus here, and all that means is that I'm taking my reference input and subtracting the output. So in this case, if this was 65 miles per hour, and this was 60 miles per hour, I'm going to return the difference of those of 5, and we're going to call that our error. Okay, so that's how far I'm off from where I want to be. And my whole goal is to drive that error to 0, right? So in the airplane example, maybe I'm measuring a position. I have a target waypoint I want to be. I'm going to measure where I'm at. I'm going to feed it back and then get an error. Maybe that could be in terms of heading, how far, or it could be in terms of distance or something, okay? So now that I have this error, what I want to introduce is the controller. Okay, the controller goes between here. It's going to take in that measured error and decide what to do. Based on what it decides, it's going to provide new system inputs. In the car example, it's going to say, you got to push on the gas more, or you got to ease up, or in the airplane example, you're going to have to actually turn further to the right, right? Maybe more than we originally planned because we're sensing that information, passing it back, seeing what the error is, controller's making a decision, providing new inputs, passing that back to the system, and then this process is just going to keep continuing, trying to drive this error down to 0. Okay, so this is the process. There are many approaches to this. I'm going to just talk about one briefly. And I mean many processes in terms of how we design this controller. I'm going to talk about one that's called PID Control. stands for proportional integral derivative. We'll see why in a minute. So again, we're focusing on this controller part. It's taking in an error, and from that error, it's deciding what inputs to give to the system. Okay, so let's think of an example here. Let's do an airplane example. So let's say I've got an airplane. Okay, so here's my airplane. This is a really horrible looking airplane, but whatever. And it's flying at this altitude. And I've got this new desired altitude. I want it to come up and fly at this new altitude. Okay, so there's some target altitude that I want to reach. Okay, so that's my reference input. That's the R. And my Y, my system output is the altitude I'm at. So I'm measuring what my current altitude is. I'm going to compare those. Now in reality, the input to this is probably is generally going to be a combination of, say, throttle and elevator. But just to keep it simple, we're going to think of just elevator. So I'm going to change the elevator on the back of my airplane. Right, that's going to be able to change the pitch of my airplane and help me to climb. And I want to get the elevator to change throughout this process so I can climb up and kind of level out at the new altitude that I'm trying to get to. And our input is actually not going to be elevator, but we're going to call it, it's going to be the change in elevator. So how much should I change my elevator? And if you think about it, it's a bit more intuitive. That's actually how we normally process things. If you can think of yourself as the controller. So imagine you're driving and you're adjusting a steering wheel. We don't think about, oh, I need to get to this angle, right? So 14 degrees or whatever, right? We think about, I need to go more to the right or a lot more to the right or a little to the left. So we're thinking about changes relative to a current position. So our input is going to be this change in elevator. So delta E for elevator, okay? So that's our input. Let me erase this. This is our reference is going to be some altitude desired, right? This is our desired altitude. And then Y is going to be our altitude that we measure. I'll just call it altitude. Okay, that's what we're going to measure. And so the error of those, right, the difference between those is going to be the error that we're going to measure. And based on that error, we're going to try and decide how much should we change our elevator. Do we need to pitch up more or do we need to pitch less? What should we do? Okay. So the simplest approach we might think to do is to design a controller, right? So again, let's think about the controller. Input is the error in altitude. Okay, let's call this E. And then the output is delta E, my change in elevator. Okay, the simplest possible relationship we could do is just to say, well, let's just make the change in elevator proportional to that error. Okay, maybe the two E's are an unfortunate choice, but this is error, this is elevator, they're not the same thing. Okay, and this K here is what we call the gain. And this kind of goes back to what I was talking about at the beginning with the car. If that gain is really large, that's going to be like, if we're going too slow, we slam on the gas, or if it's too small, it's going to be like we barely press on the gas and slowly ease forward. So this is what that roll is. And so you can see what's going to happen here, that as that error is large, right, if I'm really far away from where I want to be, maybe I need a bigger change in elevator. And as I approach where I need to be and the error is small, I don't want to change my elevator very much, okay? This could work. It'll probably cause us to overshoot, but you could see that at least if we were able to get there and the error was 0, so we plugged in an error of 0, then the change of our elevator would be 0. And assuming that was at the right elevator setting, you know, then we could just keep going, right? We'd be able to fly at that altitude. In practice, probably the proportional controller is going to have us change our elevator up to climb. We're not going to change it as much anymore, so we might overshoot. We may have to go negative. It might oscillate a bit. It's probably not going to be not going to work super well to get to a position. If we were trying to get to a desired speed, actually this proportional controller worked quite well, but perhaps not so much for just trying to get to an altitude, but it may work. So that's a proportional term, but this is, like I said, the simplest and often not sufficient. Generally is not going to do a good enough job. So as an example, let's say that the conditions are, we've set our gain, right? We kind of chose a gain, we've tuned it based on experience, but that may not be enough. So let's say we're flying now at a higher altitude, the density is less, and our engines aren't producing quite as much thrust as normal. Maybe we're carrying more weight than normal. Perhaps there's some wind, there's a downdraft, and for whatever reason, it's taking us much longer to climb than normal. Okay, so even though we've got a set proportional controller and it's going to work towards it, its response time may be too slow, or it may not respond to some of these changes very well. So another thing we could do, so you can imagine if we were to illustrate that, here's time, and ideally, and here's say my error. Ideally, right where our error is pretty high, we're far off from where we want to be, but it slowly drops down and we get towards say a 0 error, and hopefully try to maintain that. It could be though that on another day, right, because we're having a hard time climbing, our process is really slow. It's just taking us a long time to get there. And we want to design a controller that's going to be maybe more robust to that. So what we could do is we could add an integral term. So we could say our change in elevator is going to be proportional to the error, and we're going to put a p here. So this is going to be the gain for the proportional term. And then we're going to add another term for the integral term. So this will be ki, another gain we need to choose. And we're going to use the integral of our error over time. So basically, we're going to look at the area under this curve. So early on, it's going to be 0. It's not going to do anything. But as this grows, right, as the area under this curve grows, this term is going to grow. And so I'm going to produce, I'm going to try, or I'm going to change my elevator more. And so I'm going to be a bit more aggressive, right? And I may, you know, even though it's taking me longer, I'm going to accelerate down further. Something like that. Okay, so that's one way to think of it. Perhaps a more classic illustration of what an integral controller could do. It's maybe easier to see with, let's say, a quadcopter. Say I was on the ground. This will just simplify it because we can think of this one-dimensional process. I've got this quadcopter and it produces some thrust, and I want to get to this desired altitude. Okay, if I had just a proportional controller, I could say, okay, my thrust, the input that I want to provide to the system is going to be proportional to the error in my altitude. Okay, so that seems like that should work great. Here the error is really big, so I'm going to provide a lot of thrust, accelerate, and as the error decreases, I'm going to decrease my thrust. Okay, so that all sounds good, right? That I should approach my altitude. The problem with that is that I'm never actually going to reach my desired altitude. So think about why for a moment. See if you can plug into that equation and think about how that would work. So imagine that I'm at my desired altitude. Like say I just somehow got there. What's my error? Well, my error in that case is 0. So that this equation says, oh, my thrust should be 0. So then I'm immediately going to fall, right? So I'm never actually going to get there. What's going to happen is I'm going to, my error, right? Let's say, well, let me put it this way. As I increase the gain, it's going to get me closer. My steady state altitude is going to get closer to this altitude. Like I'm going to say stop right here. I'm not going to go any further. As I increase that gain, that point's going to get closer, but it's never going to get to 0. And we can see that because let's say I move this gain up, then there's going to be, the point I'm going to stop at is when, you know, my forces are balanced here. Say my thrust is equal to my weight. So let's say this is a constant here. There's a target thrust that I need to get to a balanced altitude. So as I increase the gain, that means I can decrease the error to reach this sort of constant. But I can never get this error to 0. That would require an infinite gain, right? You know, that's not really going to make sense. So I can never quite get that error to 0. And like we said, if we did somehow instantaneous get to 0, our thrust would go to 0 and we'd drop. And so this proportional controller is never going to quite get us there. Conversely, though, if we add an integral term, then what's going to happen again is that our error, you know, is going to start high, it's going to drop, but it's, oops, let's do that. It's going to be at some finite value, right? And if we only had a proportional controller, it's just going to stay at that finite value forever, and it's never going to get closer. But now this integral term is building up, is capturing that area of that curve. And so it's going to want to drive this to 0. So now, because of that integral term, it's going to keep going. Let's say I turned it on here. It's going to now try and get rid of this error and bring me down to 0. Until my error is 0, right, this integral term is still going to keep pushing. But once I get to 0, then this term is 0. And this integral term is going to give me the right proportionality constants to maintain my thrust, right? Because it's going to be this area under this curve. It's going to keep going until I get this area under this curve to just provide me the thrust that I need. So I can stay balanced at the altitude I want with thrust equal to weight, right? So obviously I need to kind of choose a proper balance, not just in K, but in proportional versus integral control. The last sort of term is a derivative. And briefly, you know, we talked about this airplane example, right? So again, here's my amazing airplane of my block airplane. It's going to come up to this altitude. And because both of these terms, these proportional term and these integral terms, they don't say anything about the rate I'm going. Right? There's this desired altitude. What they're just trying to do is to get there. And so proportional term is going to decrease as I get closer, but it's still going to be changing elevator. So likely I'm going to perhaps have some overshoot. The derivative term is looking at the rate. So we could write it this way. If in this case, this was a delta elevator that we're going to change. It's proportional to the error. And then maybe we have the integral term. And then we're going to have another gain for a derivative term. It's proportional to how much my error is changing in time. So we're looking at the rate. You could think about this if you were driving a car and you were trying to pull into a parking spot. A derivative term is kind of going to think about the rate, right? So you don't just go really fast, try to get there, and then maybe overshoot and come back and then slowly settle into that spot. When you drive, you're thinking about, okay, I'm coming in too fast. I need to ease into it, right? So you're thinking about that slope. Is my speed too high? Am I coming in too fast? Is my error changing too quickly? I need to anticipate that and start slowing down. So here where the error, for example, is dropping really fast, this will provide a big negative term. And so this term is going to actually counter some of these. So instead of having just this big gain where we kind of overshoot and go too fast, it's going to ease us in. And so again, obviously there's a proper balance between these. And this is what we call tuning the controller. It's going to take, you know, some good data and testing and some good models to figure out what the appropriate gains are. Okay, so again, this is just kind of a simplified, and again, this altitude thing is a bit oversimplified, but just trying to illustrate some of the concepts. The way this is looked at, you'll remember that earlier in the class when we were looking at stability, we plotted the eigenvalues on the complex plane. Right? We spent some good time on that, and you did that in X-Flyer, and you were able to see, is my airplane stable or unstable? And so that is what we would call the open loop dynamics of the airplane, meaning there's no controller. Is it open loop stable or unstable? Now with the controller, you can plot them both in what's called a root locus. Same thing, we plot it on the complex plane. You could think of it this way. Now I've got kind of my controller / system together as like one big system, right? Where I've got input versus output. So I need to look at the dynamics of the combined controller system. And we plot on the root locus, we can then see, you know, stability characteristics and things like that. And like we talked about, that's how you could make an unstable system, a stable that was open loop unstable. But by adding the controller, you could make it stable. You could bring those eigenvalues over to the left half plane, right, to where it could be stable. So that's one way to look at it. Another way is in a frequency plot. So this is what's called a Bode plot. We'll plot the dynamic response on a frequency plot. Another thing that's looked at, well, I guess I got a little space here. Another alternative control method is a state space. So we could think of, and this is particularly useful if we've got multiple inputs and multiple outputs. So we could say the dynamics of our system, we can write in a matrix form where this would be just the dynamics. So like we could be relating velocities, positions, and accelerations to velocities. This dot means a derivative in time. And then we would add our control input. So for example, this U here, might be not just changing elevator, but we could put changing elevator, changing aileron, maybe changing throttle or whatever, right? And in this case, we could have, depending on this size, this matrix would really depend on how many outputs we have. But let's just make it square just for purpose of illustration. Then I could have a bunch of gains, right, that I can choose rather than just one. So I can have a more complex system. And then of course here there's going to be my dynamics. This might be my angles, right, my pitch, my yaw, and my roll and things like that, right? And their derivatives. These are things that are going to populate in the dynamics. Anyway, we're not going to really get into this. I just want to say, just in brief, that this type of form can give me more options in the sense that I can have multiple inputs and multiple outputs. It's a little more complex, so we often, as a first control, this is still widely used. We use this PID control. And again, PID stands for proportional. We got this proportional term, integral, and derivative. And these are widely used in many applications, obviously not just airplanes, but many types of systems. But there are more complex forms like the Statespace form. So anyway, this is a very brief intro to controls. If it's something you're interested in, like I said, there are many courses and quite a bit more depth you could dive into. All right, we'll see you next time.